Hello! In this video, we will see how to use partial fraction decomposition to solve integrals of rational functions. Remember when you first learned how to add fractions together? And let's think of an example here. Let's take 2 divided by x plus 1 plus 4 divided by 3x minus 2. How would we add these fractions together? Well, we would find common denominators and then add them together. So to get common denominators, we'll multiply the first fraction by the denominator of the second. Numerator and denominator, we multiply. And then in the second fraction, we multiply numerator and denominator by the denominator of the first fraction, x plus 1 over x plus 1. So let's go ahead and do this. In the numerator, we'll distribute in the first fraction. 3x times 2 is 6x minus 2 times 2, 4. In the second fraction, we have 4 times x plus 4 times 1. And the denominator is the common denominator that we just found. Both fractions have the same denominator of 3x minus 2 times x plus 1. Let's go ahead and simplify. In the numerator, we have a 6x plus 4x, that's 10x. And minus 4 plus 4 cancel. And then we can FOIL out the denominator. We get 3x squared minus 2x plus 3x is a plus 1x. And then negative 2 times 1 minus 2. So adding these fractions together, we get this rational function. Let's think of reversing this procedure. What if we started out with just a single rational function and wanted to split it apart into two separate rational functions? That's what we're going to focus on here. So to add fractions, we find common denominators. In this section, we will reverse the procedure to split a single fraction, one rational function, into many partial fractions. Now, you might think to yourself, well, why would we be interested in doing this? What's the point of taking a rational function and splitting it up into multiple rational functions? Well, we'll take a look at that question in example 1. Here we have a rather complicated looking rational function. And it turns out that we can decompose this rational function into these partial fractions. If we were to add these fractions together, we would obtain this rational function. Now, suppose we want to integrate this rational function. Suppose we want to find its antiderivative. We cannot do that directly. In general, we don't have a rule for the antiderivative of a fraction. So how do we integrate this? Well, the answer is we first break it apart into the partial fractions, and then we separately integrate each one of these partial fractions, and that would give us the integral of the entire thing. Now, at this step, don't worry about how we decompose the fraction. We'll talk about that later. But let's just focus on the concept here of taking a complicated rational function and splitting it apart in order to find antiderivatives. So I went ahead and copied down those functions, and now let's think about integrating. Once again, the original rational function cannot be directly integrated. However, when I split it apart, now I can integrate. Let's take a look. The antiderivative of 2 over x is 2 times the natural log of the absolute value of x. For this second fraction, I could solve it again with natural log. It's technically a u substitution, but this is the type that we want to be able to solve without having to work through all the steps of the substitution. So this will be plus natural log absolute value of 1 minus 2x. And now if I think of taking the derivative to go backwards, I would have 1 divided by 1 minus 2x times negative 2 from the derivative of negative 2x from the chain rule. So I have a factor of negative 2 that I don't want, so I divide by negative 2. So there's the antiderivative for this second fraction. For the third fraction, we should recognize this as arctangent. So the antiderivative here, well, I have the 5 in the numerator times arctangent of x. Finally, for this last fraction, we might be tempted to use the natural log rule because we see x is in the denominator, but I don't have just x to the first in the denominator. I have something squared. So I want to think of this as x plus 3 to the negative 2 power. Once again, this is a substitution that we should do without going through all the steps. Taking the antiderivative of something raised to the negative 2 power, we add 1 to the power. So we'd have x plus 3 to the negative 2 plus 1, negative 1, divide by the new power of negative 1, and we still have the 4 multiplied outside. So that is the antiderivative for the final fraction. Add on a plus c, and we have the integral. Once again, think of the concept here. We can't directly integrate the original rational function. So we need a way to break the function apart into smaller rational functions so that we can integrate each of those separately. That's what integration by partial fraction decomposition is all about. Let's go back to the front of the handout. This concept is an example of an important theme that we've seen before in calculus. In order to solve integrals, it is sometimes necessary to first rewrite the integrand into a workable form. We might need to use some trigonometric identity. We might need to use some algebraic technique, such as this partial fraction decomposition that we're talking about here. But there's some step before we attempt to do the calculus, before we can find the antiderivative. This is a very important concept in calculus. Before we can actually do a calculus technique, such as an integral or derivative or what have you, we first need to rewrite our expression using some algebra, and then at that point, we can do calculus. So how do we do that? How do we take a single rational function and split it apart so that we can take antiderivatives? Let's talk about that next. So we're thinking of taking a rational function. We have a polynomial divided by a polynomial. Ultimately, we want to integrate. But before we can integrate, we need to decompose the rational function. Well, the first thing to do is to check the degrees of the numerator and denominator. And if the degree of the denominator is not larger than the degree of the numerator, we would need to do a polynomial long division. We will not see examples of that, but in general, that's something that we'd have to look out for. In the examples that we take a look at, the degree of the denominator will always be greater, so we don't have to worry about this polynomial long division step. All right, so the first thing to do is to take the denominator and factor it as much as we can. We factor into linears and irreducible quadratics. Turns out that you can always factor a polynomial over the real numbers into linear factors and irreducible quadratics. So that's the first step. Now, how do we figure out if a factor is irreducible quadratic? Well, that means that we can't factor it any further, and it's irreducible quadratic if the discriminant is less than 0. This expression is called the discriminant, b squared minus 4ac. And if we're not sure whether or not our quadratic is irreducible, we look at the discriminant. Once we've factored, then we write out the form of the partial fraction decomposition. And we'll practice determining what these forms are like. But for each factor, we write a fraction. And when we have linear factors in the denominator, we write just a constant in the numerator. And for irreducible quadratic factors, we put a linear in the numerator. And when we have repeated factors, we have to repeat the fractions, and we'll see examples for how to do that. Once we have the form of the partial fraction decomposition, we solve for these constants a, b, and c. Once we've done that, we will have successfully decomposed our original rational function into partial fractions, and at that point, we can then integrate. So let's practice. Let's take a look at example 2. We want to write out the form of the partial fraction decompositions for these rational functions. So the first step is to just double check that the degree of the denominator is greater than the degree of the numerator. In the first example, we have degree 2 downstairs, so that's good. In the second example, I have a degree 2 in the numerator. In the denominator, well, if I multiply the 3x squared times x, I would have degree 4. So this denominator actually has degree 4, which is greater than the numerator, so that one's all right. And then we have, in this last example, degree 1 in the numerator. The degree of the denominator is larger, so there's no long division necessary. All right, back to part A. First thing we need to do is to factor the denominator. In general, if we don't see a way to factor, then we should use the quadratic formula. However, on this one, I think I can factor. It looks like this factors into x plus 6 times x minus 2. If we FOIL that out, then we get the x squared plus 4x minus 12. Once I've written out the factorization, I'm ready now to write the form of the decomposition. I have two factors, so in my decomposition, I'm going to write two fractions. In the first fraction, I put the x plus 6. In the second, x minus 2. These are both linear factors. So in the numerators, I will just put a single constant, a and b. This is the form of the partial fraction decomposition. Let's take a look at the next problem. The first step is to factor, but x times x minus 1, that's already factored, so the only thing we need to check is the 3x squared plus 4x plus 5. Can we factor that? Well, if we're not sure, we could try the quadratic formula, or if we're suspicious that it's irreducible, then we can try to take the discriminant. The discriminant is b squared minus 4ac. So this is a, b, c. b squared minus 4ac. For this example, b is 4, so we have b squared 16 minus 4 times a, that's 3, times c, that's 5. 4 times 3 times 5, if we multiply that, it's 60. So 16 minus 60, this is negative. When we have a negative discriminant, we have an irreducible quadratic, so I cannot factor any further. All right, so I'm ready to write the form of the decomposition. I have 3 factors, so I'm going to write 3 fractions. The first one has a denominator of x, the next one has a denominator of x minus 1, and then the last one has the irreducible quadratic, 3x squared plus 4x plus 5. For each of the linear factors, I put a single constant in the numerator, a, b. For the irreducible quadratic, I put a linear factor in the numerator, cx plus d. Now, we didn't repeat any of the factors. We only have a single multiple of each factor. In the next example, we'll take a look at how to deal with repeated factors. So let's do that now. In the second example, we just want to double check real quick that we can't factor the denominator any further. So the x squared, this is as factored as we can get. X plus 1, that's factored already. What about x squared minus 9? Well, we might recognize that as the difference of perfect squares. I can factor x squared minus 9 as x minus 3 times x plus 3. So that portion can be factored. How about this last factor, x squared plus 4 squared? This is irreducible quadratic, and if we wanted to check, we could use the discriminant again. The discriminant is b squared minus 4ac, and for this example, b is 0. There's no middle term here. So we have 0 squared minus 4 times 1 times 4, minus 16, that's less than 0, so we cannot factor this final factor. All right, so let's write the form of the decomposition. Each factor will get its own fraction. So I have a factor of x squared. It's a repeated linear. This will give me 2 fractions. The first one has a denominator of x. The second one has a denominator of x squared. The factor x plus 1 cubed, that gives me 3 fractions. The first one is something divided by x plus 1, and then something divided by x plus 1 squared, and then something divided by x plus 1 cubed. Notice how this repeated linear factor gives me 3 fractions in the decomposition. And then I have 2 linear factors. Each of those give me 2 fractions. So I'll have plus something divided by x minus 3 plus something divided by x plus 3. And then finally, I'm at the last factor, which is an irreducible quadratic that's been repeated. Since it's repeated twice, I'll get 2 fractions. The first one has a denominator x squared plus 4. The second one has a denominator x squared plus 4 quantity squared. All right, so we have a lot of linear factors that were repeated. Each of those fractions will just get a single constant in the numerator. For the irreducible quadratic fractions, I will have linear terms in the numerator. All right, so we fill in the constants. We essentially have to sing the alphabet song. A, B, C, D, E, F, G. There we go. These are all the linear fractions. The next fraction has a quadratic in the denominator, irreducible. So instead of just having a single constant in the numerator, I have hx plus I. And then in the last fraction, once again, I have quadratic in the denominator. So I have jx plus k. This is the form of the partial fraction decomposition for this rational function. If we were to continue on with the problem, we would want to solve for the constants a, b, c, d, etc., which would be rather involved for this example, but we'll see how to do that with some simpler examples.